Hi, I'm Donna Perigin from Jacksonville State University, and today we'll be discussing gas chromatography mass spectrometry as it is discussed in Chapter 15 of the Klein Organic Chemistry textbook. So this is Chapter 15. This is section 15.8 in the Klein textbook, and mass spectrometry is the topic that we're going to talk about today. And first of all, I'd like to talk about how mass spectrometry is used and what it's used for. So mass spectrometry is used primarily to determine the molecular weight of a compound, or the molar mass of a compound, and hopefully its molecular formula. And so we're going to learn to determine the molecular formula from the given molar mass, which is indicated by the mass spectrum. And so this is also used in industry or like in forensics labs to not just get your molecular formula, but to actually get the real formula for the compound, so the actual structural formula, by running a spectrum against a library of known compounds, and then the machine will actually spit out the formula for the compound that or the actual structural formula for the compound that is being sampled. And so you might say, well, why do I need to know this then? Because there could be a library that I can run all these compounds against, and I won't even need to know how to do this. The computer's going to do this for me when I'm actually out there in the job. Well, that's not completely true, because every day there are new compounds being discovered or being synthesized, especially in clandestine drug labs that are trying to get around the law by synthesizing derivatives of active drug compounds. Those may not come up in a library. There may be something similar in the library that can give you a hint of what you have, but the actual molecule may not be there. So we're going to learn to use mass spectrometry just as one tool in our toolbox of integrated spectroscopy to help us determine the molecular formula and give us some keys about how that molecule is put together. So what is mass spectrometry? So it's used primarily as a detector for another instrument called a gas chromatograph. So this GC instrument actually separates the compounds into their individual components, and we're going to talk about that a little bit later on. And then these components each hit the detector, and that detector is actually a mass spectrometer, and that is what we're going to talk about now. So how does the mass spectrometer work? Well, the compound is injected into the instrument, and usually this is done by an auto sampler, and we have one in our department. It can be done manually. The compound is injected, and then it's vaporized, and then it's hit, it's ionized somehow. Usually it's hit by an electron beam, and we'll see that in just a minute. And then the masses of the ions that are created there are detected in graft. Okay, so this is what the instrument kind of looks like here. So the samples are injected into a port, and then they're heated in the sample chamber, and then they're usually hit with an electron beam so that they are ionized, and we'll talk about how that works. Then the carrier gas carries them through this magnetic field where they are deflected. The ions will be deflected, and they'll hit the detector, and they'll hit the detector according to their mass to charge ratio. So remember, these are ions, and normally the ion is going to be in a +1 state. And so if the ion has a +1 charge, then mass divided by 1 is just going to be the mass. And so we get the mass of those ions hitting the detector at different points in our spectrum. So we'll see that some of the parts are actually not ionized, and those don't hit the detector. They just keep going in a straight line instead of being deflected by the magnetic field. So those parts would not actually hit the detector, but the charged species will hit the detector according to their mass to charge ratio, and then the computer analyzes that and gives us a spectrum. So how does this work? Well, our molecule is injected into the instrument and hit by a beam of electrons. So this is a very high energy beam of electrons, about 70 electron volts, and it can cause an electron to be ejected from the molecule. So what happens if a molecule loses an electron? If it loses an electron, it's going to become a radical because it's lost an electron, so that electron is no longer paired. It's missing an electron, and because it's missing an electron, it's going to have a +1 charge. So electrons have a -1 charge. If it's missing an electron, it's going to have a +1 charge. Okay, so we've formed a radical cation. The radical cation represents what's called the molecular ion. So our molecular ion, and that can be represented as an M+ dot, or our M+ for molecular ion. Okay, so here we have this again. We have a beam of electrons hitting our molecule, forming a radical cation. If the radical cation remains intact, then that will go ahead to hit the detector as the molecular ion with the molecular weight of the molecule. Why? Because the electron that was ejected basically has a negligible weight. It doesn't count toward the molecular weight. So we can actually get the molecular weight of the molecule if it remains intact by doing this procedure. So we get the molecular weight of the molecule as the parent ion. And usually that molecule is also going to undergo some type of fragmentation, and we'll see that fragmentation pattern also as part of the spectrum. So we're going to see hopefully the parent ion intact, and we're going to see parts of the molecule also in the spectrum, so fragments of the molecule. So the molecule can fragment, and when it does, it's going to fragment into a radical and a cation. So the cations are going to be deflected by the magnetic field, and the radicals will just keep going straight through the magnetic field undeflected. So we're going to be detecting the cations but not the radicals. Not the not the uncharged radicals. Alright, so the most important piece of information that we can get is the molar mass of the compound, and therefore the molecular formula. So we're going to see how to use mass spectrometry to calculate the molecular formula.